Welcome to NPTEL Power System Protection course. We are on module 4 directional link. Today's lecture is on Poity sequence based directional link. Here we will talk about how Poity sequence voltage and current information is useful for obtaining the direction of fault. Last class we discussed about how sequence component can be also useful for obtaining the direction of fault. Modern relays use the angle information of voltage and current phasors to decide on direction of fault. Some relays use the impedance, Poity sequence, negative sequence and zero sequence obtained from the corresponding voltage and current phasors. So, we have three varieties of such relays: Poity sequence, negative sequence and zero sequence relays based on sequence components. 67 positive, 67 negative, 67 zero sequence are for the overcurrent directional relays with the corresponding sequence components. We will go one by one. First, we will go with Poity sequence approach, but before going to that, let us see the sequence diagram and from there we will derive the corresponding directional link principle. Same system, 3-bus system to understand the concept. So, at bus n M we have this relay and it is forward looking in this direction. The corresponding current through this relay will be I m n. Now, fault happens to be there in the system at F 2. For this relay there is a reverse fault. So, for this reverse fault the different sequence component for this system, this is Poity sequence network, negative sequence network and zero sequence network. This we have already learned in our basic on sequence diagram perspective. So, here if you see, this is the fault point F 2 to the left of this M bus and the corresponding impedances of source, this line section from F 2 and the other portion of the, you can say that ML line is Z F M 1 and this is the line section M n. So, the corresponding Poity sequence impedance is Z M n 1 and this side source is Z S n 1 Poity sequence impedance and then the corresponding voltage. Similarly, corresponding negative sequence impedances are here and so also the zero sequence impedances in the zero sequence network. Note that these two, can say that networks negative and zero sequences are passive networks, they do not have any voltage source here, only the Poity sequence network contains the sources. Now, consider that the fault is a 3-phase fault, the reverse fault for the relay R M n, then we say that it has only Poity sequence component and associated with a fault resistance of R f. So, we put Z f in generic. So, Z f equals to R f here with the corresponding sequence network for fault F 2 reverse fault for 3 phase, the corresponding network becomes like this. Now, when this corresponding fault happens to be phase to ground like A G fault, B G fault or C G fault, then in that case we know that the positive, negative and zero sequence networks will be connected in series with fault resistance being R f, 3 R f will be connected. So, what you see here that to this positive sequence component part where we have the voltage sources, the negative sequence and zero sequence, these components are connected in series along with the 3 R f. Note that because the corresponding current will entering to this zero sequence or negative sequence will be divided into 2 paths. So, therefore, when you find the equivalent for this negative sequence or zero sequence, we have 2 parallel paths. So, equivalent of these two parallel paths for negative and 0 plus the 3 RF is nothing but the corresponding impedance added between this point and this point of the Poetic sequence network. So, we say that if you take the equivalent of this passive portion as ZF, then the corresponding equivalent of this network become like this, what you have seen for 3-phase network. This is phase to ground fault connection, series connection of positive, negative and 0 with 3 RF. Now, this portion we can take an equivalent like parallel here, combination of these two in series plus 3 RF is nothing but this ZF, equivalent ZF. So, if you put this between these 2 points, then this becomes the ZF and the rest is nothing but the Poetic sequence network. Similar network we got in case of the 3-phase fault also. So, thus we can say that for phase A to ground fault in the forward direction, if we do now F1 fault, then the fault becomes here, and in similar way we can put the positive, negative and 0 sequence network with 3 RF in series, and then we can get the corresponding equivalent network, Poetic sequence network and equivalent ZF, combination of negative, 0 and 3 RF series connection will be the equivalent ZF, and the network connections will be like this. So, in general we saw that for the 3-phase fault or for the line to ground fault, the equivalent network of the 3-bus system becomes like this, where we put a ZF for the passive portion at the fault point and the rest is the Poetic sequence network. In case of line to ground fault, as we have already discussed, that the 3 RF will be series with the parallel equivalent of the 0 sequence and the parallel equivalent of the negative sequence, and these you can say that constitute the ZF, this part. Similarly, for 3-phase fault, this RF constitute the corresponding ZF. Now, for other faults, phase to phase fault and the double phase to ground fault, the corresponding sequence network for the corresponding ZF equivalent becomes like this and this. So, this is obtained from the positive and negative and the corresponding negative and 0 sequence component of this equivalent system. In case of line to line fault, we do not have any 0 sequence component. In case of double line to ground fault, we have 0 sequence component also. So, that leads to conclusion that for all types of fault, the system sequence diagram can be considered as an equivalent like this with the Poetic sequence diagram, and at the fault point we can have a parallel path of ZF, where ZF consists of these you can say that elements depending upon the type of fault. Now, we will come to based on that Poetic sequence equivalent diagram, how you can exploit the directional link principle we will see. Note that before going to the principle, the Poetic sequence components are available for all types of fault, that is its strength. So, let us consider a fault in the forward direction F1, then the solid fault. So, then the corresponding this is a 3-phase bolted fault, then the Poetic sequence diagram and the corresponding ZF, the ZF becomes equals to 0 here, because this is a bolted fault, and this F1 is the forward fault in this case. Now, see here, if you write the equation for this equivalent system for this fault case, 3-phase fault case, then we see that the relay voltage at here will be V 1 m, 1 for the Poetic sequence, m for the m bus relay. V 1 m equals to, this is F1 point is having 0 voltage because bolted fault. So, therefore, the corresponding voltage in this portion is I 1 m n Z m m f 1, Z m f 1 the corresponding impedance of this portion, and the I 1 m n the positive sequence current through this path is I1 Mn, and that is what the relay current also. So, therefore, this voltage is 0. So, to calculate this voltage, so we are going against the current. So, therefore, V 1 M equals to I 1 M n plus Z M F 1. So, this leads to consider that from this relation we can say that I 1 M n divided by V 1 M equals to 1 divided by Z M F 1. So, defining phi 1 for the positive sequence, the angle between the current, the corresponding current I 1 M, and that is the corresponding current which is flowing through the relay, minus the angle of this relay voltage, that equals to, if you from this relation if you see that the negative of the angle of the Z M F 1, where Z M F 1 is the impedance of this portion from fault to the relay. So, that is what nothing but the impedance of the line, So, we say that the impedance of the line being positive, if we see that for this forward fault which we are considering, the phi 1 will come to be a negative value. It means that for forward fault, because this is the equivalent for all types of fault, for forward fault we can say that the phi 1, which is nothing but the angle of positive sequence current seen by the relay minus the angle of the positive sequence voltage seen by the relay R M n will be equals to a positive value, because this is a forward fault. This is the conclusion we see from here. Now, one point here, in practical RF may not be 0 for different faults, for line to ground faults it may be higher value. So, in that case what you say that if RF becomes higher, if this becomes the fault path current, so this path becomes more and more resistive with higher and higher RF. That means that the corresponding angle which we will talk about, angle of this will go decreasing, but typically here if we see the corresponding impedance angle will be 80 degree and so for the overhead transmission line and so maybe more also. So, therefore, even you can say that with RF value the corresponding angle decreases, but still we see that the corresponding phi 1 will be negative in general. That is the what we say that. So, in general we say that for a forward fault the phi 1 which is the angle between the corresponding current, positive sequence current and the positive sequence voltage will be negative. Now, let us come to in terms of phasor diagram, how can you interpret this. So, let us, this is our same 3 bus system, forward fault, we got the equivalent diagram to be like this. So, we have L bus voltage E L, current is flowing from left to right, N bus voltage E N, and in between we have M bus voltage, let us say V M before the fault, V M pre. Now, what happens if fault happens to be there, any fault, equivalent becomes like this. So, now the corresponding V fault at that bus decreases. So, this is decrement. Now, we compute the from this V A, V B, V C the corresponding V 1 M fault, positive sequence at fault. Note that when we are computing the V 1 M fault, so V A, V B, V C will be available, and we orient V B and V C towards A phase, that is 1 plus alpha V B plus alpha square V C, 1/3 of that. So, that results in your positive sequence voltage. So, therefore, at that time the corresponding voltage will be to the pre voltage, it will be close to that and somewhat lower depending upon the dip in the voltage. So, this leads to this corresponding situation like this. Note that the corresponding fault current will lag the corresponding V M pre or V M fault. So, therefore, it is lagging, and this is you can say that the corresponding current, and this current whatever type you can say that from this perspective we see that this current will be lagging in this path. So, therefore, we see that the current I 1 M F N lags the V 1 M fault. This shows that the phi 1, the angle of I 1 minus the angle of V 1 for the relay bus at the relay bus, that becomes negative. because current is lagging the voltage, corresponding current is lagging the voltage. Now, come to the reverse fault. This was reverse fault F 2. For this situation, the corresponding equivalent diagram based on the Poitou sequence network will be like this, with the ZF corresponding thing depends upon the type of fault and the RF. Here in this case again EL, EN and Vm the pre-fault voltage. So, now the corresponding V1m fault somewhat lower. So, obtained from VA, VB, VC. Now, the current at this relay is fair to consider from the EN source and there is a reversal of current. So, therefore, this will be current will be reversed, that we have already seen in case of the phase quantity based directional link. So, current will be reversed. So, current will be upward. And that means that this I 1 MFN leads the corresponding V 1 M fault, and therefore, we can say that we can say that the corresponding phi 1 will be positive in case of here, that is angle of I 1 minus angle of V 1. So, we say that as compared to this is a lagging current, this is a leading current. So, phi 1 will be positive in this case. So, we conclude from this that for forward fault phi 1 computed in this manner will be negative, and for reverse fault the phi 1 computed in this way will be positive. Note that based on these phasor diagrams, these angle phi 1 is limited to 0 to plus minus 180 degree. That has to be seen in case of the calculation. So, this we say that Poitou sequence based directional relay can be obtained from the angle phi 1, which is equals to angle of I 1 minus angle of V 1 at the relay bus. So, let us see an example for the 9 bus systems, which we have already discussed in case of phase quantity based directional link. So, the relay R 1 and R 2 are there for at bus 8 and bus 9 for the line section 8 and 9. Fault is at F 1. For relay R 1, this is the forward fault. For relay R 2 also, this is the forward fault. Now, let us see from the data. So, this case is for the phase A to ground fault, AG fault created at this point with a fault resistance of R f equals to 1 ohm. So, what the relay finds? Currents I A, I B, I C, I A 0.53, I B 0.11, I C 0.10. It means that these are pre-fault currents and this is the fault current. So, there is a load here, that is why these currents are in other phases. Now, see the voltages now, V A voltage now 26.78, V B and V C are much higher than these are the close to the rated voltage. This is substantially low, it means that the fault is in phase A. Based on this I A, I B, I C, I 1 and using V A, V C, V 1 computed. So, we got the corresponding angle here. Now, what you need, you can say that is now that angle of I 1 minus angle of V 1 will be the corresponding phi 1 angle. So, angle of I 1 is minus 160.5 and angle of V 1 is minus 95. So, angle of I 1 minus angle of V 1. So, minus 160.5 plus 95. So, that gives us minus 65.51. So, this is the angle phi 1. This angle is negative, implies the fault is in the forward directions. So, therefore, from this computation as seen by the relay R 1 here, then the corresponding phi 1 angle indicates that the fault is in forward direction, which is correct. Now, let us see what the relay R 2 sees. The relay R 2 finds a measurements I A, I B, I C like this. We compute I 1 using these 3. Similarly, from V A, V, V C we compute V 1 and then we got the I 1 to be an angle of minus 141.65 and V 1 minus 93.2. So, angle of I 1 minus 141.65 minus this angle means plus 93.20, that gives us minus 48.45 degree. So, this also says that the angle is negative, implies the fault is in forward direction as seen by the relay R2. So, R2 also sees the fault in forward, and this is correct as per our logics we put, you can say that in the last slide. So, the conclusion for these two relays from the sets of measurements, either the fault is in forward for both relays. So, therefore, you can conclude that it is inside the line 8 and 9. Now, we will go to another case, fault is beyond line 8 9, that is R2 will see still it is a forward direction, but R1 will see it is a reverse direction. Now, let us see how they evaluate the corresponding fault situation. So, for R1 the corresponding currents set is like this, and the corresponding voltage sets available here. You see VA phase voltage is substantially low. Now, if you compute the corresponding I1, this becomes having a magnitude of 0.21 and angle of 32.41 degree, a positive angle. Now, V1 80.61 with a negative angle of 95.37. So, angle of I1 minus angle of V1 32.41 plus 95.37 gives you 127.78 positive angle. Positive angle of I1 means reverse fault, that we have seen, because this is less than 180 degree. Now, coming to the R2 relay, for the same case set of currents and we have set of voltages, computed the I1. The I1 has an angle of minus 141.4 and the corresponding voltage, sequence voltage has an angle of minus 91.96. So, angle of I1 minus 141.4 plus 91.56 gives you minus 49.83. Minus angle means this is a forward fault case. So, for R2 this is a forward fault case, this is also correct. So, we conclude that the R1 and R2 correctly identified the fault, R1 finds it as reverse fault and R2 finds it as forward fault. Now, we have another case on this evaluation of the directional relaying using positive sequence components. So, we increase the corresponding RF value to be higher, and we already mentioned when RF value becomes higher, the corresponding path in the positive sequence diagram we see that becomes more resistive. So, that is why the angle is expected to go down, that from the angle of the impedance angle of the line. So, let us see for this F1 fault which is forward to both R1 and R2, how the corresponding relaying principle performs. Current sets are set is available here, corresponding positive sequence current with a minus 52.71, corresponding voltage VA, VB, BC, V1 and this minus 99 point this. So, we see that minus 52.71 plus 99.16 gives you 46.45 degree. So, the angle is positive angle. Positive angle means reverse fault, but this is not correct. R1 should see as forward fault. So, this reverse fault is seen by this, because phi 1 is positive is incorrect, erroneous, and the reason being now we have only increased the fault resistance, and that is the reason you can say it is coming out to be positive value, and then there is a pre fault currents and so in the system. Now, relay R2 we have set of currents, set of voltages, positive sequence current and positive sequence voltage computed, minus 188.55 degree plus minus 97.23 degree minus 21.32. This is positive, means forward. So, relay R2 sees the fault in forward direction still. Note that as compared to the earlier case, the corresponding angle for R2 also has come down, and this is due to only because of this RF. So, this means that the phi 1 is affected by this RF, we have already mentioned, and we found that substantially high value of RF may lead incorrect decision. That is what the conclusion from this observation table. So, we see that Poetis sequence based directional laying can be obtained, and this is based on this kind of equivalent sequence diagram, Poetis sequence diagram, but we observe that due to the when the RF value becomes significant, then the corresponding decision by the relay may be affected. This happens particularly for the line to ground fault involving grounds. Furthermore, because the fault current which will be going through this ZF path, in addition to that there is pre-fault current in the system, the current which will be observed by the relay is a combination of the pre-fault current or the load component of current plus the fault component. So, therefore, the corresponding current which is seen by the relay during fault is being modulated by the load component of current. So, when this load component of current becomes significant as compared to the fault component, then also the modulation to the current phasor and the corresponding angle may be significant, and sometimes that also may affect significantly. So, that is relay. I relay equals to I pre-fault plus I fault, and if the pre-fault becomes significant, that may also affect the directional link performance using the Poetis sequence component. Thank you.